When you've completed this lesson, you will be able to apply the Pythagorean theorem to solve problems and use trigonometry problems and their inverses and know when to apply them. Photonics technicians need to use trigonometric functions. A famous Pythagorean theorem is related to that because it has right triangles in it, and it's very useful for solving object problems. In addition, you will use several trigonometry functions to solve object problems. For example, the sine function, the cosine function, and the tangent function. Now, on your calculator, you may recognize those as sin, cos, and tan. So you may have wondered what those functions were. Well, today you're going to learn about how to use them to solve problems. You've already encountered some of these functions in previous modules, for example, Snell's law of refraction, which says index of refraction 1 times the sine of theta 1 is equal to n2, the sine of theta 2. And so you may have already used that function. Now you'll learn how to relate it to right triangles in geometry. So let's look at a scenario. U.S. astronauts back in the very early days of the space program placed a 1 squared meter retroflector on the surface of the moon. It was designed to reflect back a large percentage of all of the light that struck it coming from the Earth, for example, a laser beam. So if scientists were to point a laser with a beam divergence of 1.35 milliradians at that panel, and the Earth is about 4 times 10 to the 8th meters away from the moon, what is the laser beam's diameter when it reaches the moon? And if the laser emits a huge beam with a 50 joule pulse in 1 microsecond, that would be 5 times 10 to the 7 watts, what power per unit area will strike the panel? And what solid angle does the lunar reflector panel present to the laser back to the scientists on Earth? Well, let's review some of the trig skills that are involved in solving this problem before we actually tackle these questions. So let's learn about some right triangles. Right triangles contain a right angle, that is 90 degrees. You've seen that before. You've learned about right triangles in previous modules. The right angle is formed by the 2 legs of the triangle. And the side opposite of the right angle is always the longest of the 3 sides, and it's known as the hypotenuse. Now, you probably remember the Pythagorean theorem and its formula where we have the sum of the 2 legs squared equals the hypotenuse squared, better known as a squared plus b squared equals c squared. This mathematical relationship between the 3 sides of a right triangle is very useful. Okay, so let's go ahead and take a look at example 1 using Pythagorean theorems. So your car odometer shows that you drove 1.8 miles up a straight road, climbing up a long hill from sea level to a sign at the top of the hill that says you are now 1 mile above sea level. Well, it's probably hard to imagine that this is really happening, but let's say for the sake of this problem that it could really happen. So how far did you travel horizontally in order to get to 1 mile above sea level after driving 1.8 miles? So let's go ahead and draw a sketch of the problem. When you're working on geometry problems, you should always draw a sketch. So we can see here that we drove up the road here 1.8 miles and rode 1 mile during that drive. So what we'd like to find is how far did we drive horizontally. So we notice that leg 2 is 1.0 miles and the hypotenuse, which is c, is 1.8 miles. And so we can use the Pythagorean theorem to solve for a. So a squared plus b squared equals c squared. And if we substitute in the values for b and c and square them and solve for a, which means that we'll subtract 1 mile squared on the right side, we'll have 3.24 squared miles and 1 square miles. So we go ahead and subtract those two to 2.24 square miles and take the square root of both sides, and we'll find out that A is 1.5 miles. So we drove 1.5 miles to get to the top of that hill. So here's an interesting fact that the text points out that we'll spend just a minute or two on. The Pythagorean theorem has been known universally and has fascinated men centuries as a squared plus b squared equals c squared. So there's a very interesting relationship between those 3 numbers. One interesting and often useful fact that you can use because you can remember them easily is that the presence of three integers that happens to work out perfectly for Pythagorean theorem. Those are called Pythagorean triples. The most famous is the 3, 4, 5 triangle. For example, you know that a 3-foot by 4-foot triangle has a hypotenuse that's 5 feet long. So that's very useful when you're framing and constructing things. And if you want to verify that something's a right angle, you can actually measure out 3 feet and 4 feet on the two sides and see whether it's 5 feet between the 2 points that you've measured. Now, there's actually quite a few Pythagorean triples. Here are 16 primitive Pythagorean triples that have less than 100 as the c-value. Now, there's also integer multiples of each of these, which would also be triples, but they would not be considered what we call a primitive. For example, 3, 4, 5 is a primitive Pythagorean triple, but we can multiply each of those by 2 and we'll have 6, 8, 10, and that's also Pythagorean triples. There's lots of Pythagorean triples, even under c is less than 100. But we've just shown 16 of the primitive ones here. So let's take a look at example 2, a real-world example where we have to find the distance between two pulleys. So we have two pulleys on a conveyor belt positioned at 9 inches apart horizontally and 6 inches apart vertically as shown. So what we need to do is find the distance between their centers. So right again, we'll draw a little sketch here and label it, and we'll see that we have 6 inches vertically and 9 inches horizontally. Those are two legs of our triangle, and we can use the Pythagorean theorem very quickly to solve for c, the diagonal distance there. A squared plus b squared equals c squared. We'll substitute the 6 inches and the 9 inches, square the two values, and add them together, and you can see here that we have to put the square root of both sides to solve for c, and we have that 10.8 inches is the distance between the two pulleys. Now, angles have a special relationship with right triangles as well. So we'll go ahead and look at that. So suppose we have a triangle that's labeled A, B, and C, and the angles inside them are also labeled as A, B, and C. And for angle A, we'll notice that there are some conventions that we need to learn. So the side opposite of angle A is known as side A, and the leg opposite angle A. And the side that's next to angle A is the leg adjacent to angle A. It's usually known as B because it's opposite of B, and the hypotenuse is C. And then there is the important trigonometric ratios that you must learn that are related to that convention and that description. So if we have the tangent of angle A is equal to the ratio of the length side opposite of A and the side adjacent of A, and you'll notice that we abbreviate it as OPP for opposite and ADJ for adjacent. There's the ratio known as the sine of angle A, and that'll be the ratio of the length of the side opposite of A to the hypotenuse of that right triangle. So if we have three sides of this triangle, and we have the angle A, and the sine is known as the ratio of the length of this side of the triangle divided by the length of the hypotenuse, opposite over HYP, abbreviation for hypotenuse. And lastly, we have the cosine ratio, which is, as you probably guessed, the ratio of the side adjacent to angle A divided by the hypotenuse. So you can see that we've got that triangle pretty well covered. So we have the ratio of the legs, the ratio of the opposite leg of the hypotenuse, and the ratio of the adjacent leg to the hypotenuse. So that pretty much covers it for angle A. Now let's look at the use of that in a real-world example. Suppose we have a car rear window which is slanted up, and we can measure how far it rises and how far it runs over that same distance. So if we can measure that the rise is 10.5 inches and the run of 12 inches, we need to find the angle that the window makes with the vertical. The first thing we'll be asked is to sketch the triangle form and calculate the value of the tangent of the angle, and we need to use our calculator's inverse function to find the angle of the measure. First of all, we need to always make a sketch and label it around what we've got, so we can see that we've got the glass is playing the role of the hypotenuse in this triangle, and the two legs are 12 inches on this side and 10.5 on this side. And here are the angles that we're trying to find. So where's the opposite side for this angle? Well, 12.0 inches will be the opposite, and 10.5 will be the adjacent. So when we know the opposite and the adjacent, What ratio is this a clue that we will probably be using? Right, the tangent function, because the tangent equals the ratio of the lengths opposite of the side divided by the adjacent side. Now you're going to remember those equations, right? So we set up our relationship. The tangent of G is equal to the opposite over the adjacent. Divide 12 over 10.5, and we can calculate that in our calculator, and it comes out to 1.14286. Now that we know what our tangent ratio is, we can do just the opposite of the tangent and use what we call the inverse tangent. Now we can always look at a table or a calculator. So for example, we had tables of tangents of all these angles, and we'd say, okay, so if our tangent is 1.14, then we would probably have to come up and down here to find the angle value that's close to that tangent. Well, we live in the modern area now where we have calculators that have all of those tables built into them. So we can find, for example, the tangent of 40 is 0.84. Conversely, when we know the value of the tangent, we can find the angle that would produce the ratio using the inverse tangent function. So if we know that it's 0.84, then we can say, oh, the angle is 40. So in this case, we have our ratio of 1.14286, and so we can look at our table and can we see 1.14? Well, we don't have it, so we can use our calculator function instead, and the inverse tangent function of the tangent will give us the angle, and the inverse tangent function of 1.14286, a ratio from our previous slide, is 48.8 degrees if we round it. So that looks like it's somewhere between 45 and 50 on our table. So our calculators made it a lot easier, so we didn't have to go through any interpolation process using our table. So we can say that the glass makes an angle of about 49 degrees with the vertical. So let's take a look at example 4. A manufacturer recommends between 65 degrees and 80 degrees for the angle a ladder makes with the ground. So anything above 80 degrees is too dangerous, and anything below 65 degrees is too dangerous. So you decide to position your ladder 3 feet from the vertical wall. Surely that looks like the right angle, but let's see if it really is or not. So we can do that with our trigonometry. So we need to find the maximum and minimum base distances for safe use, and then compare that to the 3-foot distance that you're planning to use. So first, as always, make a sketch of the geometry of the situation. We have our angle B and our triangle, which is the angle between what the ladder makes with the ground, and that's supposed to be between 65 and 80 degrees. We have our 24-foot ladder standing up from the top of the wall, and we have adjacent to that angle our 3 feet, how far our ladder is away from the wall. So knowing the adjacent and hypotenuse lengths of a triangle means that we can calculate the cosine ratio. Remember that? So when the 24-foot ladder is 3 foot from the wall, the cosine of the angle B will be equal to the adjacent length divided by the hypotenuse length, which in our case is 3 feet divided by 24 feet. The feet will cancel and we'll have a ratio of 0.125. So now, what angle would give a cosine of 0.125? So to do that, we'd have to use the inverse of cosine function. So we press the inverse cosine of the value of cosine B, which we know is 0.125, and the cosine inverse of 0.125 equals 82.8 degrees rounded. Now, unfortunately, this is outside the recommended range of 65 degrees to 80 degrees, so we must conclude that our 3-foot ladder placement is unsafe because it produces an unsafe angle. It's too steep. So it means that it's too close to the wall, so we're going to have to move it back away a little bit in order to get less than 80 degrees. So what distances would be safe? So let's go ahead and work that problem the other way then. So we know that the hypotenuse and the angle values, and we need to find the adjacent side length. Again, we'll use the cosine ratio. So we'll set up the ratio for the minimum and the maximum angles and solve for the unknown adjacent length. So the adjacent length in this case would be 24 feet times 0.4226 is the cosine of 65 degrees, and we know that that'll be the maximum distance, and that'll be when the ladder is almost flat. And 10.1 feet would be the answer that we would get from the farthest distance away from the wall that we should have that ladder. Alright, so let's go ahead and look at the other extreme. If 80 degrees, the cosine of 80 is equal to the adjacent side divided by 24. And we'll solve for the adjacent. And that'll be 24 times the cosine of 0.1736. And that evaluates to 4.2 feet. So that means that it can be as close as 4.2 feet and no farther than 10.1 feet. So unfortunately, 3 feet is just too close. Now let's return to our opening scenario with the laser and the retroreflector located on the moon 4 times 10 to the 8th meters away, so that's 400 million meters away, and the laser beam divergence of theta equals 1.35 milliradians, not a very large divergence, so maybe that laser beam isn't too big when it gets there, and the laser output of 5 times 10 to the 7th watts, 15 megawatts. Alright, so let's find the beam diameter when it reaches the moon. So as always, let's go ahead and make a sketch of the geometry. And so we have the Earth and the moon, and the beam is spreading with an angle theta. And we'll label those coordinates and those points as A, B, C, and D. And you'll notice that we have a triangle. That's A, B, C. So let's just look at that triangle. And in that case, the angle A in that triangle is actually half of theta. So we'll say theta over 2, and the adjacent side, which is the distance between the Earth and the moon, is AC. So we know that the angle, which is theta over 2, and we have the adjacent side. Alright, so that should begin to tell you something. So we're trying to find the beam spread D as it reaches the moon. And so the opposite side of our triangle is going to be half of the beam spread. So half D. So we need to find what BC is. So the tangent of the angle, theta over 2, is going to equal the opposite side divided by the adjacent side. Now, we know that the adjacent side and we know the angle, but we don't know the opposite. So we're going to have to solve for the opposite. We can substitute in the angle that we know, which is 1.35 milliradians divided by 2. And we don't know what the BC is, and so we'll divide by the adjacent side, which is the Earth to moon distance. And we solve for BC, and we'll multiply those numbers out, and the result will be 2.7 times 10 to the 5th meters, better known as 270 kilometers. So that's a pretty wide spot on the moon, because twice of that, which is that diameter of the spot, is actually going to be 540 kilometers wide. So that's pretty huge compared to that tiny little 1 square meter retroreflector. Now assuming all of the laser's power reaches the moon and is now spread over a circular spot of diameter 540 kilometers, we can calculate what the power per unit area would be on the surface of the moon. So that'll be the incident power divided by the area of the spot, which will be pi over 4 times the diameter squared. So we substitute in our values of 5 times 10 to the 7 watts and pi over 4 times our diameter, which is 540 kilometers squared. And we'll have 2.2 times 10 to the minus 4 watts per square meter. And finally, the power that will strike that little 1 square meter panel after traveling 4 times 10 to the 8th meters is carried by a solid angle, and we can calculate as the area divided by the distance that it traveled squared. And if you remember back to our geometry unit, we talked about the solid angles. So that'll be 1 meter squared divided by the distance, 4 times 10 to the 8th meter squared. And that'll evaluate out to 6 times 10 to the minus 18 steradians. So that's a pretty small angle. Okay, so next we'll take a look at some practice exercises. As usual, we won't go through every single one of these, but just enough to give you the confidence to be able to complete the rest on your own. First of all, we have an application of the Pythagorean theorem in kind of an unusual way. We have in electronics an impedance equation that says that z squared is equal to r squared plus x squared, where z is the impedance of the circuit, r is the electrical resistance of the circuit, and x is the reactance, all of these measured in ohms. Well, that looks a lot like the Pythagorean theorem, doesn't it? So we can look graphically how that might be similar to the Pythagorean theorem. Recall the right triangle in the Pythagorean theorem has a squared plus b squared equals c squared, Or we can turn that around so that it looks like our problem, c squared equals a squared plus b squared. In which case the hypotenuse is played by the impedance, and the two legs are played by the role of the resistance R and the reactance X. Now, given a loudspeaker that has an impedance of 8 ohms and you measure its resistance to be 1.5 ohms, can we find the speaker's reactance? Well, it's simply a matter of application of Pythagorean theorem and solving for the unknown X in this case. So we'll substitute in the values for the overall impedance is 8 ohms and the resistance is 1.5 ohms, and we need to solve for X. So we'll insert the values and square them, and solve for X by taking the square root of both sides, and that'll be 7.9 ohms rounded. Alright, so now let's look at exercise 3, where the illustration here shows you a 3-foot minimum extension above the top landing for a safe ladder use. So this is a little like the problem that we saw in the example. In this case, we're going to be more realistic and say that the ladder has to extend 3 feet above the top where we step off. So again, we have a 24-foot ladder, and using the illustration guidelines, we have to find the distance to the top support A. It's clearly 24 feet minus 3 feet equals 21 feet. Now notice that the illustration is talking about the distance from the vertical, like we had from the distance of the wall in our example. Here we're showing that we'd like it to be 1/4 the distance up the ladder on the top support. So let's draw a sketch of our situation where we have a triangle where the hypotenuse is A, and we have the vertical distance h, and the leg of our triangle is 1/4 A, according to our drawing. So we have the Pythagorean theorem here that says 1/4 A squared plus the h squared will equal the hypotenuse squared, or A in this case. So we can solve for h, so that's going to be a squared minus 1/16 a squared, which we can then realize is going to be 15/16 a squared. We're still working algebraically here, so now we can go ahead and substitute in the values for a, which is 21 feet, to 15/16 of 21 feet squared. Take the square root of it, and that'll be 20.33 feet. Okay, well that concludes our treatment of Module 10, Trigonometry for Mathematics for Photonics Education. I know that we've given you a lot of stuff here, but hopefully it'll give you some confidence to go on and finish the rest of those exercises and solve the problems that you've encountered in your photonics career. All right, we'll see you next time.